Welcome back. In today's lecture, in part 11 of this lecture series, I will be discussing a few numericals based on multiple charge systems where you wish to find out electric field at given point. I'm showing this as two examples and then we'll do more numericals. In this case, there are just two charges A and B, and the question says find electric field at point P. The distance of point P from A is given to be 3 centimeters, that is 0.03 meters. From B, the point P is at 0.04 meters. Charges Q1 and Q2 are 3.6 nanocoulomb and minus 3.2 nanocoulomb respectively. You wish to find out electric field at point P. So, the question as such is not a complicated question, but we'll develop an approach. That approach will be applicable to all the complicated questions as well. That means we need to follow certain steps. How should we follow? How should we proceed rather? First of all, just put a small positive test charge Q0 from your own side at the point of observation. Wherever you wish to find out the electric field, just put a small positive test charge over there. And look in which direction it will go. That means in which direction it is experiencing force due to other charges. For example, point A has got a charge which is positive 3.6 nanocoulomb. Now this positive charge will push this Q0 in this direction. So electric field of Q1 at point P would point in this direction. Just name that parameter, let's say I call that electric field E1. So E1 is electric field at point P due to charge Q1. Similarly, what will happen due to charge Q2? Q2, whatever magnitude, it is negative in polarity. The negative charge will attract the positive test charge, so the force and hence the electric field will point in this direction. So let's say I call that E2. Now E2 is acting along PD. Once I find out E1 and E2, I'll have to do the vector sum of these two fields to get the resultant field. Had there been a third charge, I would do the vector sum of all those three. Had there been 10 charges, I will find out E1, E2, E3, so on, if they are discrete charges, arbitrarily randomly distributed, that's what I am saying. So I will have to find out electric field due to each one of them and then see if some get cancelled out or not, or otherwise I will do the simple vector sum of them. This is the approach which can be followed even to the complicated questions as far as the charge distribution is random, the arbitrary charge distribution. When there is continuous charge distribution, an altogether different approach need to be followed. In this case, we have got E1 and E2 which can be calculated very easily. What is E1? E1 would be 1 by 4 pi epsilon naught, and then charge is 3.6 into 10 raised to the power minus 9 divided by distance. Distance is 3 into 10 raised to the power minus 2 whole square. This is E1. What is E2? E2 is same 1 by 4 pi epsilon naught. It is 3.2 into 10 raised to the power minus 9 divided by 0.4, or I can write it down like 4 into 10 raised to the power minus 2 whole square. Now, the resultant electric field can be obtained as under the root E1 square plus E2 square. I know 1 by 4 pi epsilon naught is common, 10 raised to the power minus 9 is common, 10 raised to the power minus 2 the square, that is 10 raised to the power minus 4, that is also common. So what do? I write down the common terms outside this square root, 1 by 4 pi epsilon naught into 10 raised to the power minus 9 divided by 10 raised to the power minus 4. These were the terms which were common out there, and the remaining term in this is 3.6 divided by 9, 3.6 square divided by 3 square, which is 9, plus 3.2 square divided by 16. Now you can put in the value of this 9 to 10 raised to power 9, which will get cancelled out with 10 to the power minus 9 factor, and other algebraic simplification can be done. If you wish to find out the direction of the resultant field, now let's say electric field is in this direction E, you can define this angle beta, and how would you find the direction of resultant electric field? Tangent beta will be equal to this is E2 divided by E1. We have obtained E2 and E1, you can find out beta. This is how a simple question can be proceeded with as far as point charge distribution, arbitrary charge distribution is concerned. I hope it is clear to you. Now let's move on to this next question. In this question there are three charges given: 16 nanocoulomb, 32 nanocoulomb, minus 16 nanocoulomb. And one more point. Did you notice that this Q2 was given to be negative, but while solving E2 I didn't put negative sign over there? Because the negative sign was changing the direction of electric field, was deciding in which direction the electric field will act. So the direction contains that information of this charge being negative. So while calculating the magnitude, or while calculating electric field, magnitude of electric field, what do? You just put in the positive values, and in the diagram you can adjust the negative sign by putting appropriate direction of that corresponding electric field. This thing will be applicable in this case as well. The question says find electric field at B. This is the point B, and all other 3 points. Let us assume this side to be whatever. Side is, let's say, whatever. Let's say 3 meters. This is 3 meter, 3 meter, 3 meter, and 3 meter. Now we wish to find out electric field at B. The approach remains the same as we did in the previous question. What? Just put a small positive test charge plus Q naught over here. Now what will happen? Let's say I call this point B, and I have put a test charge Q naught, which is by convention is always positive. What will happen? Now 16 nanocoulomb charge, what will it do? It will push it in this direction. Let's say I call that E1. The magnitude of that electric field I am saying as E1. Now what about this electric field? Minus 16 nanocoulomb. Now minus 16 nanocoulomb will attract it in this direction. A little common sense. I need not to call it E2, although the direction is different, so it's a different vector. But in magnitude, that would still be E1. Why? The charges given are identical, 16 and 16. It's a square. The distance of this point B is also same, so that's why it is E1 and E1. What about the 32 nanocoulomb? It is pushing it away in this direction. Let's say I call that E2. Now, what will I do? I'll find out the resultant of E1 and E1. That resultant will act in this direction. Since both are equal in magnitude, it will be 45 degrees. Surely, when two equal vectors act perpendicular to each other, the resultant acts at an angle of 45 degrees, that is right in the middle of the two. And its magnitude will be what? Under the root E1 square plus E1 square, that means under root 2 times E1. So this resultant magnitude of E1 and E1 is under root 2 E1. Once I have calculated this, now I need to find out resultant of under root 2 E1 and E2, because there are 3 charges. So to find out the vector sum of 3 vectors, what I have done, I am taking the first 2, finding out their vector sum, and then whatever the resultant of the first 2 was there, and now I will take its vector sum with the third vector. So under root 2 E1 and E2 need to be again summed up vectorially to find out the resultant electric field at point B. First of all, see what this electric field E2 would equal to. Would be equal to E2 would be equal to the constant of proportionality 1 by 4 pi epsilon naught. For simplicity, I am just writing it down as K. Then the charge, which is 32 nanocoulomb, 10 raised to the power minus 9, divided by, if this is 3 meter, this is 3 meter, this distance will be under root 2 times 3 meter. Simple Pythagoras theorem. 3 square plus 3 square under the root. So 3 times under root 2 square. This turns out to be K times 32 into 10 raised to the power minus 9 divided by 18. This is the magnitude of E2. And what was the other vector? Under root 2 E1. What was E1? E1 was the constant of proportionality K times the charge. Charge is 16 into 10 raised to the power minus 9 whole divided by what? Whole divided by the square of the distance, which is 9. Now what would be the angle between E2 and under root 2 E1? Need not to tell you. This was 45 degrees, so this is 45 degrees. The resultant angle between this resultant vector and E2 vector is still 90 degrees. So what would be the final resultant? What would be the final resultant electric field? It will be the square of the first vector plus the square of the second vector under the root. That means under root 2 E1 square plus E2 square, which turns out to be 2 times E1 square plus E2 square, which turns out to be 2 times E1 square. E1 square is K into 16 into 10 raised to the power minus 9 divided by 9 whole square plus E2 square. E2 square was K times 32 times 10 raised to the power minus 9 divided by 18 whole square. What we obtained? I can see a few things common out here. What are the common things? K is common. 16, and here we have got 32. 16 into 2, this is again 32 and 32. So K is common, 32 is common, 10 raised to the power minus 9 is common, and in denominator we have got 9 over here and 18 over here. So what can I do? I can take out 9, and what would remain inside would be factor 2 over here, and square of 2, it will become 4. Under root contains, this whole term is out of the square root, so I have got just 1 plus 1 by 2 square. This can be further solved. You can put in the value of E as well, K as well, which is 9 into 10 raised to the power 9 into 32 into 10 raised to the power minus 9 divided by 9, 1 plus 1 by 4. Whatever get cancelled, just cancel it out. But what you get is 32 times under root 5 by 2 newtons per coulomb. This is the resultant electric field. This is the resultant electric field at point B. Now, I'll show you a few questions. I'll just simply write down the questions. You note them down and solve them, and you can put their answers in the comment box. Make sure that you solve all those questions. Solve these questions. Let's say an equilateral triangle. Find electric field at the center. The side is say A. Charges are Q, Q and minus Q. Side is A. It's an equilateral triangle. Side is A. And you wish to find out electric field at the center. The three vertices have got charges Q, Q and minus Q. try this one. A square of side A, charges are plus Q, and minus Q over here. You wish to find out electric field at this point. This question seems similar to that, a little different. Solve this question. You have got a pentagon. Q, 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 Q. 4 points have got charge Q. The fifth point does not. The fifth corner of the pentagon does not have any charge. You wish to find out the electric field at the center. Take side A. It would be interesting to solve. Thank you.